So I just got this new PASCO weather sensor. I'm super pumped for this. I just couldn't wait to try it out and show you guys. Let me first show you what we have here. This is the weather sensor. Very portable. You can carry it around. It's like a mini weather station. And this is the wind turbine for the anemometer to measure the wind speed. Right beside it, there's the sensor for the measurement of temperature, relative humidity, and barometric pressure, which are the main measurements I will be focusing on most of the time. There's also a GPS sensor located right on top of the temperature sensor. You're not able to see it, but you have this indicator light. When flashing green, it means the GPS sensor is communicating with at least 3 satellites. And on the very top, you also have the light sensor that measures UV index and illuminance, stuff like that. So right after I got the weather sensor, just couldn't wait to try it out. I set it up in my backyard, put it on a stake to elevate it from the ground. And with this experiment, I'm focusing on temperature and relative humidity. So I have to make sure the sensor is not directly exposed to sunlight. Otherwise, you wouldn't be able to get accurate readings of temperature and humidity. That's why you see it's in a sheltered place. There's a roof. And of course, this will affect wind speed or UV index, some of the other measurements, which I'm not gonna look at too much for this experiment. And I set it up at 8:20 p.m. and have it run for about 4 hours to 12:33 a.m. Okay. I got really exciting graph and data. Let me show you. So first, let's look at the measurements the weather sensor can take. Actually, there are 19 of them. Okay, some of the common ones like temperature, humidity, dew point, wind speed, and some of them, like even it has a wireless compass built in. It gives you the magnetic heading and true heading, and also it has the GPS sensor that measures latitude, longitude, and it actually gives you a satellite count as well. I'll show you that in a second. I find it very interesting. So let's take a look at the temperature data first. And you can see, let me change the time to hours. You can change the units for all the measurements to your desired one. So the temperature, you can see it decrease at night from 8:20 p.m. To 12:30 a.m. And let's do a linear regression here to find out the decreasing rate. So you can see the slope of the line is negative 1.92. Okay, so that means the temperature decrease by 1.9 degree every hour. Okay, and let's say we add another measurement. Relative humidity. And let me put them on the same scale. Right, so the purple one is the temperature, the sort of like a turquoise color line is the relative humidity, the Y2. And you can see the relative humidity actually increase at night. Oh, by the way, for those of you who are not familiar with relative humidity, I can briefly go over it. Let's go to the PowerPoint actually. So all right. Oh, in fact, by the way, I forgot to show you this. You see the light is flashing green. Yeah, that means it's connecting well to the satellite. And so let's go over what is relative humidity. It is equal to the actual amount of water vapor in the air divided by the maximum amount of water vapor the air can hold. Okay, so let me visualize it for you. Let's say at 30 degrees Celsius, the air can hold a maximum of 100 units of water vapor. And let's use this bucket to represent how much water vapor the air can hold. Okay? Let's say 100 units. And then if you have 50 units of water vapor right now in the air, then the relative humidity is going to be equal to 50 over 100, 50%. Fairly easy to understand, right? And if the water vapor go up to 70 units, the relative humidity is going to be 70%. And of course, you can go all the way up to 100 units, and then the RH is going to be 100%. And that's when we say the air has reached saturation, or the air is saturated. Okay. So that's relative humidity. And let's add in another variable. So I'm gonna add dew point here. All right, so let me put them on the same scale as well. All right, cool. So the reason I add the dew point is because to understand why the relative humidity increase at night, we need to look at the temperature and the dew point. You can see this is temperature, the green one is the dew point. The difference between them decreases. Okay? So as the temperature approach the dew point, the relative humidity can actually increase. And you see this on the graph, and let's also analyze it. And again, let me go to, all right, so this is the example we just did, right? So at 30 degree, let's say the air, if the air can hold 100 units of water vapor, and then if you have 50 units of water vapor right now, the relative humidity is 50%. Okay. However, if we decrease the temperature to 26 degree, then the amount of water vapor the air can hold actually also decrease. Let's say 80 units. I'm just making the number up for this explanation. Okay, and this is not hard to understand. So you can imagine at the equator, when the climate is warmer, evaporation happens all the time, happens very easily, because the air can take up more water vapor when it's warmer, whereas in the polar area, and there's not much evaporation going on because the air is very cold, it cannot take much water vapor. So when you decrease the temperature, the amount of water vapor the air can hold decrease to 80 instead of 100. So decrease to 80. However, if the actual water vapor, the 50 units, it's still there, then our relative humidity is going to increase, because now your denominator is changed to 80 from 100, while your numerator is the same. You still have 50 units of water vapor in the air, and then your relative humidity becomes 62.5%. And if you keep decreasing the temperature, for example, you decrease it to 19 degree, then maybe the air can only hold 50 units of water vapor. So that just means the air becomes saturated. Okay, so the relative humidity becomes 100%. And this 19 degree is what we call the dew point. is the temperature at which the air becomes saturated. Okay, and as you can see, when the temperature starts to decrease and approach dew point, the relative humidity actually increase. That's why this is what we're looking at here. And as you see, the gap becomes smaller, the difference between the temperature and dew point becomes smaller, relative humidity increase. Very neat, right? So the weather sensor is actually really, you can tell it's really accurate. And later I'm going to show you some quantitative analysis as well. So it's really powerful actually. All right, so what are some of the other variables we can look at? Okay, let me open another page. So let's say we can look at the barometric pressure. In fact, for the pressure, there's not much to look at, since I didn't really change my altitude, right? I didn't go hiking or anything like that, although I plan to do that in the future. So the pressure stayed the same, which is, I'm going to change it to a more commonly used unit, which is kilopascal, over here. So the pressure at my location is about 101.5 kilopascal, which is about sea level, because the average sea level pressure is 101.3 kilopascal, close enough. And the barometric pressure basically means you can imagine, for example, I'm just gonna use this graph. You can imagine there's 1 square meter of space on the ground. Let's say this is 1 square meter, and you can imagine an air column extending from all the way from the ground to the top of the atmosphere, okay, to the edge of the atmosphere. So the entire weight of this air column is going to be the pressure, okay. So at my location, per square meter, the weight of the air is 101.5 kilonewtons. All right, so this is what pressure means. And let's see if we have other. Okay, Humidex. All right, this is a really interesting one because this is actually a Canadian invention. We use it more in Canada. And let me first briefly explain what that is. So Humidex, right here. It describes how hot the weather feels to the average person, and it takes into account both temperature and humidity. So if you don't understand this, you must have heard of wind chill, right? Wind chill temperature. Wind chill, this is a similar idea. So wind chill is like quantity we normally look at in winter. When there's the wind outside, that will make you feel colder than the actual temperature is showing. It's very practical because what you feel is the most important thing, right? So you actually feel colder due to the wind. That's why we have the wind chill temperature. But that's more used in winter. So in summer, we use Humidex because in summer, what we actually care about is the heat and the humidity, right? So we want to take those into account. So it's not only like temperature, you also have to take into account the humidity, and that combined will tell you how you will feel about the weather, if it's nice or if it's muggy. And Humidex does that. This is the chart you can use to tell if the degree of comfort of the weather. Okay, so basically below 29, no discomfort. It's going to be nice. Over 30, there's some concerns. You may experience some discomfort. 46 over, definitely dangerous. And you can see our data shows the Humidex right now, at least at my location in Surrey, British Columbia, is pretty nice, right? Between 50 and 25, all below 29. So West Coast is pretty nice at this time. And you may get some of those on the East Coast or in the middle. And you can also figure out the Humidex from temperature and relative humidity here. So for example, if the temperature is 25 degrees and the humidity is 85%, then the Humidex is 34, which is, according to this chart, will cause you some discomfort. Right? So you can use this chart to figure out Humidex. And you can see when you go down and go to the left, it becomes rougher, right? So which means you don't want high temperature and high relative humidity. That will make you feel really muggy. Like you can see the Humidex is really high. Whereas if the temperature is cooler and the humidity is smaller, and then relative humidity is smaller, you will get really nice Humidex here. Okay. Here a technical note. Some people will interpret Humidex as the actual, like in terms of the actual degree Celsius or Fahrenheit. For example, they'll be like, this 32 means you feel the environment is 32 degrees Celsius. In fact, it's not really correct. Humidex is really what we call a dimensionless quantity, which means it doesn't have unit. You really should just look at it as an index and use this chart to help you decide the degree of comfort. However, when the temperature is low, like when the temperature is like within 20 degrees, the Humidex is really not much different from your temperature, which I will show you here. So those are Humidex, and if I add in the temperature, you can see how close they are, right? Very close, within 1 degree difference. So, right, so the purple one is the temperature and the brown one, the Humidex. Because our temperature is very low anyway, so when the temperature is low, Humidex is really close to the temperature. But if the temperature is high, especially in hot summer, Humidex really, you just have to refer to the table. No, where is it? 1 yeah, here. You just really have to refer to the table. Like 45 Humidex doesn't really mean you feel 45 degrees Celsius, but from the chart, it will cause you great discomfort. Okay. All right. What other variables we have? I'll just open another one to show you different variables. You can display all the measurements on the same like page, but because they do have different units, so I tend to open a separate page for measurements that are very different. So let's say UV index. Right, like I said, this experiment is not great for UV index, but I still want to show you something that I find that's pretty cool. Let me change this to hour. Okay, so remember I set the weather sensor at about 8:20 p.m., right? And you can see right after about an hour, the UV index becomes 0, which means no sunlight anymore, right? So that's about 9:20 p.m. And if you look up on the government website, that's matching the sunset time, which is around 9:20. So the weather sensor is pretty accurate, pretty cool. What else? Let me prove. Okay, just show you the satellite count. You can see most of the time it's connecting to about 6 to 11 satellites, right? So it'll give you the measurements of all the locations. All right, so last I want to show you some quantitative analysis that can show you what you can do with it in a math class or environmental science class or physics class. It also shows you how cool this weather sensor is. So basically, again, I'm going to go back to temperature, dew point, and relative humidity because those three actually have a quantitative relationship. Okay, so what I'm going to do is I will take a point from the relative humidity graph. Like this point is at, I don't know if you can see this, 10,450 seconds, and the relative humidity is 75.4. And then I'm going to take the corresponding point on the temperature. This is a temperature graph. So at this time, the temperature is 14.3 degrees. What I'm going to do is I'm going to plug in those two data into an equation that is used to calculate the dew point. And I'm going to compare the result with this dew point output from the weather sensor. And I want to see if they match. Right? Basically, I'm checking if the weather sensor is making sense. And of course, we need to check that, right? So the equation I'm using is, where here, this. Hold on a second. All right. Oh, got stuck. Yeah, it happens sometimes. All right, better. Okay, so there's a simplified one. There's a complicated one. I know what you're thinking. We're going to use the simplified one, but I do want to explain the complicated one because it's actually not that complicated. For anyone who have done pre-calculus 12, they can actually do this one. So the idea is to take the relative humidity data and the temperature data and get the dew point, right? And we have a system of equations here, 3 equations, and you see a lot of letters there, right? However, most of the letters here are either constant or they are measurements you take, right? So there are actually also only 3 variables. The variables we have here, I'm gonna actually circle them, is the actual water vapor pressure and the saturated vapor pressure. By the way, this is actually the more rigorous mathematical definition of relative humidity. It's equal to the actual water vapor pressure divided by the saturated vapor pressure. And those are our variables in this equation, and so is TD. Right? So we have 3 variables and 3 equations. We can solve these systems of equations for sure. See the rest of it, it looks intimidating, but really they're just constant, right? And the relative humidity and temperature, you take the measurement from our weather sensor. So if you want to use this equation, what you do is you first plug in the temperature in the 3rd equation, and from there you can get ES. And then you plug ES into the 1st equation, and with RH and ES you can get E, and then you plug E into the second equation. Now you can solve for TD, because now you know everything except for TD in the second equation. And of course you may have to take the lowering logarithm if you remember that. Alright, but now I want to talk about the simplified one. This one is this, a lot simpler than the one on the left, right? However, this is a really good approximation of the quantitative relationship between TD, T, and RH. So, and I got this equation from this paper by Dr. Mark Lawrence, published in Bulletin of American Meteorological Society, a really good journal. So let's try it out. So what we're gonna do is we're gonna take remember the, let me pull it out, humidity 75.4 and temperature 14.3, plug it into that equation, and we're gonna compare it with 9.3, right? So that's our goal. And let me actually write it out. Oh, all right. So TD is equal to, T is 14.3 minus, and RH, we're just going to take the number part, 75.4, and over 5. Okay, it's 75.4. And TD, we get 9.38. Oh my god. Do you see how close that is to 9.3? Okay, so the TD from the sensor, weather sensor, is 9.3 degree. You see how close those data is, and you can get like a percentage difference if you want. That'll give you an idea of how close they are. Percentage difference is 9.3. You can go minus, sorry if you can hear some noise, it's the kids in my townhouse complex, and divided by 9.3, that give you the percentage difference. It's within 1%. It's 0.86%. Guys, look how accurate the weather sensor is. But I have to note that the dew point is actually also a secondary measurement, which means it's also derived from the primary measurement from the temperature and the relative humidity. But still, we get the quite impressive result here. So the theory is consistent with the reality. Anyway, this is just a quick demo of what the weather sensor I just got. There's a lot more stuff you can do with it. So you can actually go to Grouse Mountain and take the weather sensor, and I'm sure it'll show you the change in altitude and even in barometric pressure, because the elevation changes a lot. And you can take it out on the field. So it's really a great tool for learning in any math or science class. So I still need to explore it a bit more, actually a lot more myself, but hopefully you enjoy this weather sensor as well.